Hello. Let's wait for just few more minutes before we start the session. I hope you can see my screen. Wait for a second. I'll just allow your microphones. All right, let's start the session. Hello, everyone. Welcome to the ninth weekly discussion and doubt clearing session of the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharjee of IIT Delhi. Um, I'm Ashirvad Satpathy. I'm a PMRF research scholar at IIT Delhi. And what I do is I take these weekly sessions where we discuss the assignment and practice problems that were given to you in the previous weeks. And we also take up any doubts that you might be having with respect to the previous week's lectures. There is another officially assigned teaching assistant to this course. His name is Debojyoti. He usually takes his weekly sessions of 2 hours um, on Saturdays from 6 to 8 p.m. And I usually take my weekly sessions of 2 hours from on Mondays from 6 to 8 p.m. But due to some issues, I had to postpone it to today. So otherwise, regularly we have the sessions on Mondays. I'll also like to inform you that I have shared the links of the previous week's lecture videos in the chat section. You can check it out, and also the lecture slides that we use during these sessions that have been uploaded to a OneDrive folder and have been shared with you in the chat section. You can always check it out. All right. In today's session, we'll be discussing the week 8 assignment 8 questions. There are around 10 questions, and the week 8 lectures were related to the strength of concrete and what I mean, we in the previous weeks we had discussed about how the cement reacts and the different types of cements and the reactions between pozzolanic materials and cement. Now in the eighth week we have discussed about cement and concrete. So how cement provides strength to concrete and other constituents like the um, uh, I mean, the aggregates and the fine and the coarse aggregates, how they contribute to the strength. How do we carry out strength tests? meaning the compressive strength test of different specimens, the tensile strength test, and what are the different effects of these different types of strength tests on the real strength or the apparent strength that we get from these tests. And so, yeah, more or less, these were the topics that were discussed with you in the week 8. And the assignment questions are also related to that. At the end of this session, we'll also like to take any doubts that you might be having regarding the week 8 lectures or any of the previous lectures, right? So the first question of this assignment was, what are the common phases in concrete which have distinct properties? Paste, aggregate, interfacial transition zone. And you have to select which of these phases in concrete have distinct properties. You do have to mention that is or are any of these options mentioned distinct phases in concrete, and if so, do they have distinct properties? I mean, they have properties different from one another. Do they have that? Yes? Can somebody answer to this question? What are the common phases in concrete which have distinct properties? Paste, aggregate, interfacial transition zone. Right, is it? I have allowed your microphones, so you can just unmute yourself and speak. Otherwise, you can raise your hand or use the chat to respond. Yes, Abdul, Vishal, Abhishek, any of you guys would like to answer this question?
That is 1, 2, and 3. All are this common phase.
Right. Okay. Yeah.
Aggregate transition zone.
So you want to say that all the three are distinct phases?
Yes, sir.
Yeah. Okay. Thank you, Abdul. Yeah, that's the correct answer. So paste, aggregate, and interfacial transition zone. All of these three phases in concrete are distinct in the sense that they do have very distinct physical and chemical properties. The concrete is basically a mixture of cement, water, and aggregates as we know it, and the cement and water constitute the paste in concrete, right? So this is the cement, or I'm also including cementitious because the concrete, the low carbon concretes or the newer age concretes are not do not just contain cement in them. They have cementitious materials like SCMs as well. So cementitious plus water, that constitutes the paste of concrete. Aggregates is both fine aggregates and coarse aggregates. And then comes interfacial transition zone. So if you want to scale up concrete, so it is like there is water, and then in water you add cement, so it becomes paste. Now you further scale it up. In paste you add fine aggregate, meaning sand, that becomes mortar. And in mortar you add coarse aggregates, that becomes concrete. Now, we need to understand that the only reactive part in concrete, majorly in most of the cases, if we assume that the aggregates are non-reactive aggregates, then the only reactive part is the cement paste, right? And when there is cement paste and there are aggregates inside the concrete, they form the boundary at the surface of the aggregate and the cement paste is known as the interfacial transition zone. You might have also studied this. This is the aggregate, and there is a boundary layer forming around the aggregates, which doesn't have the properties of the aggregate itself, nor does it have the properties of the cement paste. It has properties different from both of these phases, and therefore we consider it to be a distinct phase in concrete. So this could include like a higher water content than that of the paste, higher water, lower solids, and lower hydration products, or we could say the volume of hydration products is larger. So the low density products, low density hydration products, or volume of hydration products is higher, right? So that constitutes the interfacial transition zone. So all of these phases are distinct phases in concrete, and they have very different properties. So that's the correct answer to the first question. The second question is a kind of assertion and reason kind of a question. So the assertion is that theoretically predicted strength is more than actually obtained strength in cement paste, and the reason being, in reality, the existence of cracks and flaws within material results in early failure. So you have to answer this question by saying if the assertion is correct, and is the reason correct, and is this reason the correct explanation to the assertion, right? So the assertion here is theoretically predicted strength is more than the actually obtained strength in cement paste, and the reason that they have given is, in reality, the existence of cracks and flaws within the material results in early failure. So hence a lower strength. Yeah, which of these options are correct? Would somebody like to answer?
First one is the correct. Assertion and reasons are true, and reason is correct explanation of assertion.
Right. Thank you, Abdul. So assertion and reason are both true, and the reason is the correct explanation of the assertion given over here. So we have also seen this in the lecture slides as well. Theoretically predicted strength from the laws of how do you predict strength of a given material, which constituents of finer materials. So that you arrive at the strength by the strength per bond of between the particles in the material, right? So when there are solid particles in the cement and in concrete, they constitute not just a chemical bond but a physico-chemical bond as well. They have a physico-chemical bond as well, which is arising out of the van der Waals forces, right? So when there are two solid particles nearby, they have van der Waals forces of attraction as well as repulsion. So van der Waals forces. Then even smaller particles have colloidal forces, and so on, right? So these forces arising within due to the interparticle interactions that constitute the strength at the particle level. So the strength of a given material at a particle level is given by these forces. So if we know the strength of these forces at a particle level, and we know the number of particles in a given material volume, then we would be able to calculate or arrive at a predicted strength of the whole material given of a given volume, right? So this is like strength per bond multiplied by number of bonds in a given volume. So strength or predicted strength of a material of known volume. Let's say we have a cube specimen. So of known volume, will be equal to the strength per bond. This strength per bond could be due to chemical bonds, could be due to physico-chemical bonds, due to interparticle interaction forces as well. So the strength per bond multiplied by the number of bonds in the given volume, right? So this is the predicted strength. But in reality, we often see that there are micro cracks and flaws that remain within the material, and due to that, the real strength of the material is lower than that of the predicted strength. So this is the correct explanation to the assertion over here. So the answer to this question is the first option, right? Moving on to the third question, which of the following is reason for higher porosity in interfacial transition zone? There are four options given: wall effect, one-sided hydration of clinker, shrinkage of cement paste, or trapping of bleed water. Which of these effects result in a higher porosity of the ITZ? Yes, can somebody answer this question? We have already discussed some of these options in the previous sessions as well. We have discussed wall effect. If I can, remind you, that was when we were discussing the packing density of aggregates, and we had discussed that the wall effect causes the packing density to lower around the boundaries of the aggregates. So that is the wall effect. Then there is one-sided hydration of clinker. So that essentially means that since the aggregate is non-reactive, that we assume, so the aggregate is not taking part in the chemical reaction, but the cement or the clinker around the aggregate, that is getting hydrated. So on one side of the ITZ, there is hydration or chemical reaction going on, and the other side, which is the aggregate side, there is no reaction going on. So could that affect, could that result in the higher porosity of the ITZ? Then the third is shrinkage of cement paste. We have already again discussed this in the previous sessions. When the cement undergoes hydration, it undergoes chemical shrinkage due to the consumption of water in the hydration. So that is a self-desiccation kind of a mechanism. So this cement paste undergoes some kind of a shrinkage. Will that result in a higher porosity of the ITZ? And finally, trapping of bleed water. Does that result in a higher porosity? Yes, can you answer this question?
In IT zone, all are affecting wall effect and one side hydration of clinker and shrinkage of cement waste and trapping of bleed water. All are affecting this
Right.
IT zone.
All affect the porosity. Right. Thank you, Abdul. So yeah, that is the correct answer. Thank you. Okay. 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 Thank you. Yeah. So that's the correct answer to this question. All of these effects actually take part in resulting in the higher porosity of the ITZ. So I have taken these view graphs from the book by Mehta and Montero, and this essentially shows different examples of ITZ and the different factors that affect the the strength, the porosity of ITZ, and why. I mean, the properties that ITZ has. Why does it have those properties? So in the first view graph, you can see that this is regarding the internal bleed water. When you have bleeding in concrete, so this is when you have the concrete essentially has a very low shear strength, and the water is the water or the paste portion is segregating from the aggregates. So the aggregates are trying to settle down, and the cement paste doesn't have the strength to keep those aggregates in suspension. So the aggregates are settling down, and the water or the cement paste is rising on the top and is accumulating as the bleed water. So this is bleeding. When bleeding occurs in concrete and there are large aggregates, as we know, they are present in the concrete. This bleed water sometimes also get trapped around the surface of these aggregates, as you can see over here. These are the darker portions shown in the view graph are bleed water, internal bleed water. So these internal bleed water they accumulate across the boundaries of the aggregates, and when this bleed water, after the concrete is dried out, hardened, this bleed water would either dry out, or it will get consumed by the concrete for the hydration process. Now, after the concrete is hardened, it doesn't have it cannot rearrange itself to a lower volume, and therefore when the bleed water goes away from these areas, that leaves a void. So that results in higher voids or larger voids, and that causes an increase in the porosity of the ITZ. So trapping of bleed water is one. Then we have already discussed shrinkage of cement paste. I'll just show. All right, let's first discuss all these view graphs, then we'll come to that. I was talking about the second view graph, where um, you see that at the boundary of the aggregates and cement paste, since the ITZ has a higher porosity and has a higher unoccupied volume, so the water that is present as a film around these aggregates, this contains calcium sulfate and aluminum ions in it, right? And due to higher space availability around the aggregate boundaries, the size of the ettringite, CSH, and the calcium hydroxide particles, those are much larger. So the volume occupied by these hydrates are larger than that present in the cement paste in the core, right? You can see over here. So this is the region of ITZ, and they have schematically shown that the volume of these hydrates is much larger. Volume is larger, and here the volume of these hydrates is smaller. When this volume is larger, the density is lower, and therefore that increases the porosity of the the into ITZ, right? So when the volume is also larger, the packing is affected, as we have seen, and due to the lower packing, the porosity increases in the ITZ. The third view graph shows you that there are typical cracking maps around this. This is an SEM micrograph. So this is an SEM micrograph, and you can see that around the aggregates there are these micro cracks present at the ITZ. So this is due to, again, as we have discussed, the cracks arise due to shrinkage of the cement paste. When the cement paste hydrates, it undergoes a chemical shrinkage. So if I draw a rough aggregate, and here is the ITZ, and here are the cement grains. Now that it has hydrated, so this is the aggregate now, and this is the ITZ, but the cement grains are further pulled apart by the internal core due to the hydration process, due to the chemical shrinkage, and therefore these cracks arise at the interface between the aggregates and the cement paste, right? So these cracks at the ITZ also increase the volume of the voids, and therefore increase the porosity of the ITZ. So we discussed trapping of lead water, shrinkage of cement paste, and one-sided hydration of clinker, again, because the other side is not getting hydrated, while the cement paste side is getting hydrated, and therefore there are cracks occurring over there and increase the porosity. And again, wall effect. So we had discussed previously also, when there are large aggregates, the packing is affected, because due to the formation of these walls, the packing is affected. When the packing density is reduced, porosity increases. So all the four of these factors contribute to the higher porosity of the IT set. Right? I hope that was clear to you. Moving on to the fourth question, up to what fraction of concrete ultimate strength cracking is governed by the ITZ? Is it 65%, 60%, 70%, 75%? I mean, there is no direct relation to predict this, but this was discussed in the lecture. So if you have watched that lecture, you'll be able to answer this question. Up to what fraction of the concrete ultimate strength cracking is governed by the ITZ? Yes, can somebody answer? This is a pretty straightforward question. If you know, otherwise you don't. Yes, anyone?
In IT set zone, that is 70%.
Yes, right. Yeah, the correct answer to this question is 70%. So up to 70% of the ultimate strength of concrete, that is governed by the ITZ. So beyond that, it is the aggregate. Sometimes the aggregate also break, but majorly the aggregates don't break in normal strength concretes, and we see the failure with we see the failure surfaces around the aggregates, which is at the ITZ preferentially. So up to 70% of the ultimate concrete strength is governed by the cracking of the ITZ. All right. Moving on to the fifth question, the critical stress required for crack propagation is, and they have given these parameters. E is the elastic modulus, T is the energy required to create new surfaces, and C is the crack length. Which of these options is the critical stress required for crack propagation? Just to give you a brief introduction about the subject, if you have watched the lectures, we have seen that for a crack to propagate, if there is a hole or a crack already existing small crack within the concrete itself, if it has to propagate, then it has, when the crack propagates, there are new surfaces being formed, right? And for that to happen, the stress strain energy that is getting released due to the crack propagation has to be, I mean, the rate of the strain energy that is getting released has to be equated with that of the rate of the surface energy required for the creation of new surfaces. So this was discussed in the lecture. On the basis of that, could you please tell me what is the answer to this question? How do you calculate the critical stress required for crack propagation? Yes, anyone? Does anyone know the answer to this question? How do you calculate the critical stress required for crack propagation? Vishal, Abhishek, Abdul. Which of this is the correct answer?
Please go ahead, sir.
Pardon? Is it? What did you say?
Please go ahead. It is
Oh, all right.
not.
Okay, all right. Okay. Yeah, the correct answer to this question is actually option 2, 4 et by pi c raised to the power 0.5. And I have taken this uh, picture from, sorry, yeah, I've taken this picture from the NPTEL lecture slides. And here you can see this is the required energy. This is the required energy, right? This is the released energy, the released strain energy, right? Due to the crack propagation. And this is the required energy due to the formation of new surfaces, right? So let's say we have a crack. I'll just go to the previous slide. We have a crack already existing, and half of the crack length, just to show you the derivation, is C dash, right? This is different from the C that is given. They have taken C as the total crack length. So half of the crack length is C dash, therefore the whole crack length is 2 C dash, right? Now, for the formation of new surfaces, meaning that when the crack has to propagate, there will be new surfaces getting formed, right? So these are the new surfaces. Now, when the for the formation of the new surfaces, you have to calculate the surface energy required, and for that, there is 2c on each side of the crack. So 2c times the thickness, which is essentially unit thickness, so 1 into the surface energy per unit area, which is T. So 2C dash into 1 into T, and this is per side. So you have to multiply it by 2 for both the surfaces. So that will give you 4C dash T, which is given in the slide over here. So the required energy is 4 CT or C dash T, right? And the released energy due to the crack propagation, that is pi C square sigma square divided by E. So this is the required surface energy, required surface energy, and strain energy released due to this. I'll just mention this in two sides. Crack length surface energy per unit area, and this is unit thickness, right? Strain energy released due to crack propagation, that is equal to pi sigma square c square divided by E. So that will be pi c square sigma square divided by E, right? Now, at the critical stress is when the rate of release of the strain energy is equal to the rate of the required surface energy, right? So you have to, in order to equate the rates, you'll have to differentiate it with respect to the half of the crack length, which is C, right? So if you both differentiate it, so d by dc dash of 4c dash t is equal to d by dc dash of pi c dash square sigma square e, and that will give you 4t will be equal to 2 pi c dash sigma square divided by e. So, and from this equation, if you arrive at sigma by 4TE divided by 2 pi C dash. So that will be raised to the power 0.5. So sigma therefore is 2TE divided by pi C dash raised to the power 0.5. But the catch in this question is that here the crack length itself is C. Earlier the crack length used to be 2C, and here it is C. That means C equals 2C dash, right? And if you put that in this equation, so that will give me sigma is equal to 2TE divided by C dash equals C by 2. So pi C and divided by 2. So that will be coming on the top. So that will be 0.4TE. That will be 4TE divided by pi C raised to the power 0.5. So that is the correct answer to this question. Yeah, I hope you got the idea of it, how you derive this. 480 divided by pi c raised to the power 0.5. In this question, I mean, in the lecture slides, it was shown to you 2et divided by pi c dash, but again, the C1 or CL is the half of the crack length. This is half crack length. So if you are given with the total crack length, you just have to multiply, I mean, this, divide this by 2, and that will become as 4TE divided by pi c raised to the power 0.5. All right. Sorry. Which was that? Yeah, we were discussing this part. Yes. All right. Moving on to the sixth question. Bond between the aggregate and paste is mostly chemical and rarely mechanical. Is this a true statement or a false statement? Bond between the aggregate and the cement paste is mostly chemical and rarely mechanical. Can you answer this
It,
question? Yeah. Yes, sir.
it is because it is mechanical.
Right. Right. It is mostly mechanical and rarely chemical. So this is a false statement. Thank you, Abdul. Yeah, we have also seen that. I mean, in which, can you also tell me in which cases is it chemical as well? I mean, in which cases the bond between the aggregate and the cement paste is chemical as well? Can you give an example of that? I agreed. In most of the cases, since the aggregate is non-reactive, so the bond between the aggregate and the cement paste is majorly mechanical in nature and not chemical. But in which cases can the bond be chemical as well? That is in the case when you're using reactive aggregates. So in majority, aggregates are inert, therefore the bond between aggregates and cement paste is mechanical in nature, right? But in the case of pozzolanic aggregates or reactive aggregates with reactive silica in them, aggregates containing reactive silica, this bond can also be chemical in nature. Be both chemical and mechanical, right? So in majority of the cases, it is generally mechanical in nature, but in some cases, as in the case of reactive aggregates, the reactive aggregates also provide reactive silica to the system and therefore take part in the chemical reaction, the pozzolanic reaction as well. And therefore, the bond between the aggregates and the paste could be chemical in that case. But majorly due to the issue of alkali silica reaction, we avoid using reactive aggregates. So we generally use inert aggregates. All right. The seventh question goes like, which of the following statements is true? And they have given four statements. The first statement is, elastic modulus of aggregate doesn't have any effect on the compressive strength of concrete. The statement 2 is, grounded aggregates show better strength than milled aggregates. Ground aggregates meaning they have been ground in a ball mill or so, and milled aggregates is basically they have sawed down. So, and statement 3 is, volcanic aggregates show chemical bonding in the cement paste. Statement 4 goes, in lean concrete, maximum size of aggregate is greater than the normal aggregate. Which of these statements are true and why? Can you answer? Is the first statement true? Elastic modulus of aggregate doesn't have any effect on the compressive strength of concrete. Does the strength or the elastic modulus of aggregate affect the strength of the concrete overall? The second statement is uh, ground aggregates and milled aggregates. Which of them show better strength? Then volcanic aggregates show chemical bonding in the cement paste. Is that true? In lean concrete, maximum size of aggregate is greater than normal aggregate. What is a lean concrete? Lean concrete is a non-technical way of saying that the cement content in the concrete is low. So typically in cases where you want to keep the heat of the total heat of the structure to be low, you use low cementitious contents, or I mean, replace majority of the cement with slow reacting cementitious materials like fly ash or slag or so on, and therefore you call it a lean concrete. Let us say like in mass concreting applications, we use a lean concrete which has a lower cement content as compared to uh, I mean rich concrete in very crude terms, which is used for self-compacted concrete or in majority of the structures where they require a high flowability in the concrete. So they have to increase the cement content. So yeah, with high congestion of reinforcement and so on, like raft foundation casting or slab casting. So you want a rich concrete there. You need to increase the cement content. As the section sizes are also smaller, thinner sections. Yeah. Anyway, so in lean concrete, maximum size of aggregate is greater than normal aggregate. Is it a true statement? Which of these statements are true and why? Can you answer? Yes. Anyone? All right. The correct answer to this question is actually the statement 3 and 4. Only those two statements are true, and the first two statements are wrong. And we'll discuss all these statements one by one just to have an idea why these statements are true if they're true and why they're false if they're false. So, the first statement says elastic modulus of aggregate doesn't affect the compressive strength of concrete. And this is not true because uh, when you apply load to a concrete specimen, the load is being shared by all the distinct phases in the concrete. It is the cement paste that is also taking the load. It is the uh, aggregates that are also taking the load, and it is also the ITZ that is also taking the load. And usually, it is the phase that has the lowest strength or the highest porosity or highest amount of flaws that breaks faster, that gives up first faster, and therefore that is the governing phase. I mean that is the phase that governs the strength of the concrete. So usually it is the ITZ, because ITZ is the weakest link in the concrete if we talk about all the phases in there. And elastic modulus of aggregate, how does it affect the strength of concrete? When you apply a certain load to a concrete specimen, this load is being shared by, as I mentioned, it is shared by all the distinct phases. So if you have some material that is a higher elastic modulus, that will also take a higher share of the load. That will also take a higher share of the load as compared to the other phases, and therefore, if you have an aggregate with a higher elastic modulus, the strength that is being taken by the all the aggregates in total in as a whole will be higher, and that will in turn increase the total overall compressive strength of the concrete as well. If you have a concrete with aggregates having a lower elastic modulus, then they will be taking a lower share of the load, and majority of the share of the loads will be taken by the cement paste and the ITZ, and therefore that will break faster because ITZ is taking a majority share of the load, and that will lead to a lower compressive strength of the concrete. So this statement is not true. Elastic modulus of aggregate does have an effect on the compressive strength of concrete. So that this is a wrong statement. Then yeah, so I have taken this view graph, the middle view graph, and it shows the effect of aggregate properties on the strength. So at any given water to cement ratio, lightweight aggregates, which also have a lower strength as well as a lower elastic modulus, give a lower strength in the concrete as compared to ordinary concrete aggregates. So this is lightweight aggregate concrete and this ordinary concrete, and you can see that at a given water to cement ratio, the strength in lightweight aggregate concrete is lower as compared to ordinary aggregate concrete. So they have said that weaker aggregates exhibit lower strength, cracks propagate through the aggregate, and lowering the water to cement ratio is ineffective. Yeah, all right. So even if you try to lower the water to cement ratio, the strength doesn't get increased much, because now previously when the aggregates were stronger, the weakest link used to be the IT set. Now that you have reduced the strength of the aggregates, the cracks can now propagate through the aggregates themselves, and therefore the strength of the concrete will be lower in that case. All right. The second statement is ground aggregates show a better strength than milled aggregates, and here I've taken the third view graph from the NPTEL lectures to give you an idea of the surface roughness for different types of aggregates. So when the surface profile is milled or bored or turned or ground or lapped and polished. So lapped and polished and ground are basically uh, surface phenomenon used to reduce the size of the aggregates. So polishing is, as you know, it is polishing the surface of the aggregates, and grinding is again by adding a charge like ball in case of ball mills. So these balls by striking against the aggregates, they essentially reduce the size by striking against the aggregates and striking on the surface of the aggregates. So when you have ground aggregates, they have very polished surfaces. I mean, somewhat polished as compared to bord or milled aggregates. So you can see the roughness values in micrometers, and as you move from lapped and polished aggregates and ground aggregates to milled aggregates, the roughness values also increase. So milled aggregates are more rough as compared to ground aggregates. Therefore, um, when the surface of a given aggregate is rough, they provide a greater interlocking uh, bond between the aggregates. So let us say this is a round aggregate and this is another round aggregate. The bond due to the the shear bond between these aggregates is lower as compared to an irregularly shaped aggregates coming from a milled kind of aggregate which has somewhat of a irregular shape. Now when these two are sheared off, the bond strength is higher due to the interlocking, right? So this is milled aggregates and this is ground aggregates. So therefore, this statement is again wrong because ground aggregates will show a lower strength than milled aggregates, because milled aggregates have an irregular shape, they have a higher surface roughness, and that surface roughness contributes to the interlocking force between these aggregates and in turn increases the bond strength between these aggregates. So the statement 1 and 2 are wrong. Coming to the statement 3, volcanic aggregates show chemical bonding in the cement paste. Yes, they could show, and they generally show chemical bonding in the cement paste because volcanic aggregates, they contain reactive silica in them, and they act as pozzolanic materials, as we have also discussed in the previous lectures as well. Volcanic ash is used to be used in the old days in the ancient Italian structures as a pozzolanic material. So volcanic aggregates, volcanic ash, they contain reactive silica and alumina in them, and therefore they contribute to the pozzolanic reaction in the cement paste, and therefore not just form a mechanical bond, rather they also form a chemical bonding in the cement paste. So the statement 3 is correct, and the statement 4 goes, um, in lean concrete maximum size of aggregate is greater than the normal size. So I have taken this, the first view graph over here, to show you again. This is from the lecture slides as well. So this is the x-axis shows the increase in the max size of aggregate, right? The y-axis shows the compressive strength, and all these curves have been given for different cement contents. So the cement content is increasing. Cement content is increasing as we move from low to high in the on the y-axis, and you can see that when the cement content is low, as you increase the maximum size of the aggregate, the compressive strength somewhat increases, right? So this is the case of lean concretes when the cement content is low. As you further increase the cement content, and then keep on increasing the maximum size of aggregates, the compressive strength of the concrete increases till some a given value and then remains constant. When you go further increasing the cement content, the compressive strength increases with the increase in the maximum size of aggregates, and then it reduces as you further increase the maximum size of aggregate. So in high strength concretes, which have high cementitious content, HSCs, which have high cement contents, as you keep on increasing the maximum size of aggregates, the compressive strength will in fact reduce, right? But in case of lean concretes, which have low cement contents, as you keep on increasing the maximum size of aggregates, the compressive strength increases. So the statement 4 is a correct statement. In lean concrete, maximum size of aggregate is greater than normal aggregate, meaning that the allowed maximum size of aggregate is could be higher due to an allied increase in the compressive strength as compared to normal concretes. So the correct answers are 3 and 4. All right. Moving on to the eighth question. What is the correct uh, all right, what is the correct order of the tensile strength calculated by different methods? So this is, I probably missed it. Correct order of the tensile strength calculated by different methods. So we have discussed this in the lecture as well. There are different methods to calculate the tensile strength of concrete. Generally, direct tensile strength test is not done in concrete because of the type of specimens that you have to prepare, and um, the capping or the holding of the specimen intact while carrying out this direct tensile strength test, that is not suitable. Therefore, we go for indirect tensile strength tests like the split tensile strength test and the modulus of ruptures test, or which we also call as the flexural strength test. So this is the flexural strength test. The split tensile strength test is done on the curved side of the cylinders, and then there is direct tensile strength test, which we generally don't do. But yeah, the question asks which of this is the correct order of the tensile strength calculated by different methods, and the options are given is the modulus of rupture greater than the split greater than the direct greater than split greater than modulus of rupture, split greater than MOR greater than direct, split greater than direct greater than MOR. Which of these options are correct and why? There's a very fundamental reason to why these values are higher or lower than the other ones. What could be that reason? And which of these are higher? And what is the correct order of the tensile strength? Yes, anyone? Would you like to answer this question? Abhishek, Abdul? What is the correct order of tensile strength calculated by these different methods? All right. So the correct answer to this question is actually the first option. Modulus of rupture is greater than the split tensile strength, which is also greater than the direct tensile strength. And why is it so? I have taken this slide from the NPTEL lecture itself, and the first bullet point, if you can see, least volume is subjected to maximum tension in MOR, followed by split, followed by direct test. And that is precisely the reason why you have this kind of order of the tensile strength found out by these tests. Now, when what is the setup in case of a MOR test? So MOR test, the test setup is somewhat like this. If you are going for a 4-point loading, so it is a flexural beam setup which has two supports and then two loads at the top, right, at equal distances. So these are all at equal distances. And um, in this case, when this beam is subjected to a flexural load, it deforms like this, somewhat like this, right? This is a common beam deformation problem. So it deforms somewhat like this, and the maximum tension is coming at the bottommost fiber. So bottommost fiber has maximum tension. So only this portion of the volume, the bottommost fiber, is experiencing the maximum tension, and therefore the volume involved is very less. Comparing this with the split tensile strength, split tensile strength test, this is a cylinder specimen, and there are two plates which are putting in load, and this is a reaction coming from the bottom, right? So the fracture will go somewhat like this, and therefore the volume that is being involved in this case is the whole portion of this volume. So this is the volume, the central portion, because the central portion is experiencing the tensile load, and the central portion of the whole volume is experiencing the load, right? Comparing this to the direct tensile strength, so this is again reduced, but the central, I mean the volume involved in the tensile load is at least higher than, so the volume involved is at least higher than the MOR test, right? In case of direct tensile strength test, essentially you have a specimen like in the case of, if you know, dog bone specimens are directed to subjected to these uniaxial tensile strength tests. So this is a dog bone specimen, and this is capped at this dog bone ends and held and applied for a tension. So this is the tension that is being applied, and the whole volume is being subjected to the tension. So the whole volume is subjected to the tension. Therefore, the involved volume is again higher in the case of direct tensile strength test, right? So this is exactly why the more the volume that is involved in the strength test, the lower will be the strength. I mean that will be much nearer to the direct tensile strength, right? So in the case of direct tensile strength, whole volume is subjected to tensile stress, and therefore it has the least tensile strength. Comparing this to the split tensile strength, only the central portion of the cylinder that is directly under the plates which is applying the load, that is only subjected to the tension, and therefore it has a slightly higher strength than that of the direct tensile strength. And if you compare that to the modulus of rupture test, which is the flexural strength test, only the bottommost fibers across the whole width of the beam that are being subjected to the maximum tensile force, and therefore the volume involved in the tensile strength test is very less, and therefore modulus of rupture is gives you a much higher value than the other two strength tests. All right. So the correct answer to this question is the first option. Moving on to the ninth question, it has again two statements, and the first one is the assertion and the second one is the reason, and you have to tell if the assertion and the reasons are correct, and if the reason is a correct explanation of the assertion or not. So the assertion is moist specimen shows lower compressive strength, and the reason they have given is adsorbed water causes dilation of cement gel, lowering the cohesion and resulting in lower strength. Is the assertion true? And if it is true, is the reason that they have given that is true? If both of them are true, is the reason the correct explanation for the assertion? Can you tell me the answer? This is a very interesting question, and this has to deal with all the different types of strength tests that are prescribed by the Indian standards. The Indian standards generally, if you have noticed, they prescribe that the specimens are generally tested for their strength when they are in a saturated surface dry condition. That is, you have removed the surface moisture. There is no free surface moisture. After you have removed it from the curing tank, you remove the surface moisture and let it air dry for the surface to dry, but the core of the concrete or the inner of the concrete is still saturated. So it is called an SSD condition, saturated surface dry condition, and at that point only you test your specimens, all your specimens. So this question has a nice relation to why do we test our specimens in SSD condition and why not in a dry condition. Can somebody answer this question? Yes, anyone? Does moist specimens show a lower compressive strength? All right. So the correct answer is the assertion is true, the reason is true, and the reason is also the correct explanation of the assertion. So yes, moist specimens show a lower compressive strength, and that is due to the fact that when you have adsorbed when you're ponding the specimens or curing it in a curing tank, you have filled all the voids, the capillary pores, the gel pores, and everything is filled with water from the external source, right? And this adsorbed water on the surface of the I mean on the CSH gel, the absorbed water on the CSH gel causes a dilation of the cement gel, and The dilation meaning that um, it um, it kind of expands, or it kind of makes the particle go farther away. So it dilates the inside of the cement gel, and therefore it lowers the cohesion between the solid particles or the solid hydrates. When the cohesion is lowered, that results in a lower strength. This is again a correct statement, and this is exactly why you you carry out your strength tests when the concrete specimens are still in a saturated condition. It is not dried, only the surface is dried in an SSD condition. Because when you carry out a strength test in a dried specimen, the strength that you'll be getting is higher, right? Because there will be no adsorbed water, and therefore the dilation will be less, the cohesion will be much higher, and the strength will be higher. Why do we want to do a strength test in a moist condition? Because there are two reasons to this. The first one is that when you have a moist specimen, the strength will be lower, and therefore, if the strength that you're getting from this the compressive strength test, that is in a moist condition and that is lower, and it is sufficient enough to take up the structural loads, then when the structure is in a dry condition and it is an excessive loading, it will have a higher strength in that case, and it will sustain that load probably. So when carrying out a strength test in a moist specimen, essentially what we are doing is we are kind of adding a crude factor of safety, meaning that we are actually taking the compressive strength on the lower side of it due to the moisture in the concrete, and therefore when the concrete is dry in the actual structure, it will be able to sustain a higher load. So that is the first reason. It induces kind of a crude factor of safety in the structural design as well, when you take the factor the characteristic strength from the moist specimens. The second part is, it is very difficult for any material to be completely dried. I mean, drying process is dependent on the porosity and the pore structure of a given material. Same is the case in concrete. You for different concretes, the drying phenomena and the drying process takes very different times, right? To achieve a degree of saturation, let's say of I mean, it's very difficult to go to zero saturation levels, but yeah, let's say we want to go achieve a zero point 0.1 degree of saturation in two different concretes, one with a larger pores, meaning that the pore structure is larger and coarse, the pore sizes are higher, and in another concrete where the pore sizes are smaller, the drying will be faster in the concrete that has larger pore sizes as compared to the concrete which has smaller pore sizes, because when you have smaller pore sizes, they have higher capillary tension, right? The capillary force in these smaller pores is higher, and therefore the water for the water to come out of these pores and get dried into the environment, that will require a higher force. So higher force means higher temperature for the water to come out of that pore. So higher temperature and longer duration of that temperature. So it is so drying phenomena is dependent on the capillary force or the capillary action within the structure, and this capillary force is dependent on the pore sizes. So it is very difficult to for two specimens, two different type of concrete to achieve the same degree of drying. So in order to maintain consistency in your results, it is essential that you need to have the same degree of saturation in your specimens, and you can't achieve that by drying your specimens in the oven or so, because as I mentioned, two different types of concretes with different types of pore structure will undergo very different drying phenomena within their microstructure, and therefore you will not be able to achieve the same degree of saturation in two different concretes with the same conditioning of temperature. Like if you increase the temperature for let's say 2 hours, two specimens will not have the same degree of saturation, and therefore on the other hand, if we have saturated concretes, it is much easier to allow water to get inside the concrete as compared to dry the concrete out. I mean, to take the water out of the concrete. So it is much easier for the water to get inside the concrete from outside. Therefore, we cure our specimens, and therefore, when you cure your specimens, the saturation level of the concrete is similar in almost all of the specimens. Now, when you have the saturation levels similar, that won't affect the strength results. Only you're getting the strength. The strength is not dependent on the degree of saturation. Now it is dependent on other properties, meaning your mix design and any other parameters, but not the saturation itself. So in order to take this degree of saturation out of the picture, we carry out a strength test in moist specimens only, in saturated surface dry specimens. Because in order to compare between two different concretes, we need to have the degree of saturation similar in both the different types of concretes. We can only achieve the degree of similar degrees of saturation when we have moist specimens. If we want to dry the specimens and test them, it won't be possible to achieve the same degree of saturation. And that is exactly why, if you notice in the Indian standards as well, they have mentioned if the concrete is kept dry for long, or you have obtained a concrete core from a structure, from a real structure, then they recommend you to cure it for some time before you actually test it, because curing will allow the water to get inside the concrete and dilate the cement gel and reduce the strength and achieve the same degree of saturation in all the concrete specimens that you're carrying out the tests on, right? So this is a very interesting question, because when we come across the Indian standards, we see that the Indian standards recommend for the tests to be carried out within, let's say, 2 hours after you have taken out from the curing tank, after you have taken out the specimens from the curing tank, and the specimens must be air dried only, not heated up, must be dried in ambient air conditions, and the surface only should be dry, not the core of concrete. So it should be in a SSD condition, right? So this is the reason exactly why we want to carry out a strength test in an SSD condition, so that we'll have consistent results. We will not have the effect of saturation, right? Moving on to the 10th question and the last question of this assignment: maximum elastic modulus of the concrete. If the elastic modulus of aggregate is 40,000 megapascals and paste is 15,000 megapascals, consider volume of aggregate in the concrete to be 60% and paste to be 40%. And there is no straightforward relation to this. The correct answer to this question is actually 30 megapascals. So I've taken this view graph from the lecture slides, and you can see that the strength of the cement paste, the stress strain curve goes like this. For the aggregates, it goes like this, and therefore for the concrete, it lies somewhere in between. So this is concrete, just highlighting it. This is cement paste, and this is aggregate. So aggregates have much higher modulus of elasticity and strength as compared to cement paste, and concrete lies in between these two. So you can carry out a weighted mean kind of a calculation in order to arrive at the elastic modulus of concrete. Let's say for the upper bound, so it has to lie within a boundary. The upper bound, or the maximum elastic modulus of the concrete, could be EC equals paste volume, so volume of P into EP plus volume of A into EA, and that will be volume of paste is 40%, so 0.4 into modulus of elasticity of paste is 15,000, plus volume of aggregates is 60%, so 0.6 into 40,000, and therefore you will arrive at EC equals 30,000 megapascal. So this is EC max, right? If we want to look at the minimum, so this is the correct answer, 30,000. For the minimum, we can take as 1 by EC min equals volume of paste divided by E of paste plus volume of aggregates divided by E of aggregates, and that will give us 1 by EC min equals 0.4 divided by 15,000 plus 0.6 divided by 40,000, and therefore EC min will be equal to how much? 1 divided by 0.4 divided by 15,000 plus 0.6 divided by 40,000, and that will be 24,000. So EC min will be 24,000, right? So EC is greater than equal to EC min and is less than equal to EC max. So EC will lie between 24,000 and 30,000 megapascals. So the correct answer, they have asked for the maximum elastic modulus, so the correct answer to this question is 30,000, right? So that concludes the assignment questions of session week 8. If you have any questions or doubts, then we can discuss them now. The session will go until 8 p.m. So if you have any doubts, then we can discuss them. Otherwise, you are free to leave. And we'll have our next session on Monday, on coming Monday from 6 to 8. I'm muting myself for now. If you have any doubts, you can just unmute yourself and speak, Abhishek, and I'll respond. Otherwise, yeah. Oh, all right. Abhishek has already left. So I guess there are no doubts. We can just close the session for today, and we'll meet again on next Monday from 6 to 8 p.m. Thank you.